Last time we explored the derivative of power functions. So when you have basically x raised to some power. Today we're going to extend that to general polynomials and also introduce the power down rule. So when you have a polynomial, we'll use a lot of examples. So if we have a polynomial such as x to the 7 plus 18x squared plus 3x plus 12. So we can basically use the linearity properties to extend the derivative of power functions to general polynomials. So we saw that the derivative of x to the n is just n x to the n minus 1. We also saw that the derivative of the sum of two functions is just equal to the derivative of the first plus the derivative of the second. And also that when we have a constant, say a times f of x, the derivative is just a times f prime of x, just like that. So we can use our rule for power functions coupled with these two linearity properties to take derivatives of arbitrary polynomials. So here is an example of a polynomial. We have a polynomial like this. So let's take the derivative. So f prime of x, and this is basically all you have to do. So here we have a power function, x to the 7th. So the 7 gets knocked down up front, and then the 7 drops down to a 6. So the derivative is equal to 7x to the 6. The next term is 18x squared. Now the 18 is a constant, so because of the second rule, the 18 can move either side of the derivative at once. So we can basically just ignore the 18 when we take the derivative of this term. So basically we're just looking at x squared. So the derivative of x squared is 2 times x, and we multiply the 2 by the 18. So the 18 just gets carried along for the ride. So 18 times 2 is 36, so we get 36x. Going on to the next term. Again, the constant is just along for the ride. 3x, the derivative of x is 1, so the derivative of 3x is just 3. It works just like that. So we get 3. And then the derivative of 12 is just 0, because it's 12 times x to the 0. When the 0 comes down, we get 0. And also the derivative of a constant is 0, because constants don't change. They have 0 slope. So the derivative of this polynomial is just 7x to the 6 plus 36x plus 3. Let's do another example. So suppose that we have the polynomial x to the 100 plus 3x to the 20 plus 4x to the 10 plus 5x cubed. Again, term by term, you differentiate each term individually, and you use the basic rule where we take the power and we drop it down for each term. So this 100 just comes out front. You knock it right down, and we get f prime of x, 100 x to the 99. So you drop 1 from the 100, the 100 comes down, and you take 1 from the 100, and it becomes the 99. Then plus, next term, the 20 comes straight down, and you multiply it by the coefficient, which is 3. 20 times 3 is 60, so we get 60x to the 19. Plus, next term, again, the 10 comes down. 10 times 4 is 40x to the 9. And then the 3 comes down. 3 times 5 is 15x squared. So that's exactly how you compute these derivatives. Let's do another one. X to the 8 plus 7x to the 7 plus 6x to the 6 plus pi. The derivative, 8 comes down out front, so we get 8x to the 7. 7 comes down, so 7 times 7 is 49, so 49x to the 6. 6 comes down, 6 times 6 is 36x to the 5th. And the derivative of pi is 0, so the derivative ends right there. And that's how you compute derivatives of polynomials. Next, let's look at the power down rule. So this is the extension of the rule, the basic derivative rule for a power function as applied to when you have u of x to the n. So we have the derivative of u of x to the n is equal to n u of x to the n minus 1 times u prime of x. So basically you just treat this as an unknown blob to the nth. The n comes down out front to the n minus 1. You do exactly the same thing you would do with the power down rule, except when you're done this time you multiply by the derivative of the inside. So whatever is inside your parentheses, you have to multiply the whole thing by the derivative of that. So let's see how it works. And why is this true? Well, this is basically the power rule, so the derivative of a power function, combined with the chain rule, which we'll talk about later, but the purpose right now is just to introduce how to use the chain rule. So if we have f of x is equal to x to the 100 plus 7x to the 7 plus 32x squared plus pi squared to the power 100. That's going to be a big polynomial, right? Because you have x to the 100 multiplied 100 times. So that's something like x to the 10,000, I think. So you could actually factor this out, just like when you FOIL, when you have two binomials and you FOIL and you get the quadratic equation. You could multiply this out 100 times and then take the derivative just like you would any other polynomial. However, I would recommend never to do that because it would take forever. So instead we have the power down rule, which is the one I wrote up here. So basically we can treat the inside, so this is the inside function like this, like a single piece, and we have this piece raised to the 100th power. Well, how do you take the derivative of that? Well, it's just 100 times that piece, x to the 100 plus 7x to the 7 plus 32x squared plus pi raised to the 99th power. So you just power down the 100. The 100 comes out front, and then we drop 100 down to 99. Just like you would 1x to the 100th, it's 100x to the 99th. Here we have u to the 100th, so it's 100 u to the 99. The only difference is that once you've done this step, you have to look at the inside stuff and multiply it by the derivative of the inside. So we multiply this by the derivative of whatever we have inside. So the derivative of the inside is going to be 100x to the 99 plus 49x to the 6 plus 64x. And the derivative of pi is 0. So it's 100, this stuff raised to the 99th, times the derivative of the inside. So it's times parentheses 100x to the 99 plus 49x to the 6 plus 64x, just like that. Let's do one more example. So suppose we have f of x is equal to x squared plus the square root of x to the 6th power. F prime of x, 6 times x squared plus the square root of x to the 5th power, and then times the derivative of the inside, which is 2x plus, there's the square root of x again, that's x to the 1/2, so it's 1/2 x to the minus 1/2. The minus kicks it downstairs, and the 1/2 means it's still the square root. So it's just like that. Remember, 1 over root x is just x to the minus 1/2. So that's it.